Iranian from the Sham University, Malaysia, and currently studying mathematics and applied mathematics. Today, I will give my presentation about the Cauchy integral remainder formula. And first of all, let's look at the summary. We'll first have the definition of the Cauchy integral remainder formula, and then we'll recap the first fundamental theorem integrating derivatives first, in order to have the proof of the Cauchy integral remainder formula. And then let's first look at the definition of formula from the textbook. According to theorem 8.70, the Cauchy integral remainder formula is defined by I be a neighborhood of the point x0 and n be a natural number. Suppose that's the function f, whose integral is from I to a real number, has n plus 1 derivatives, and that the n plus 1 derivative whose interval from I to R is continuous. Then for each point x in I, we have this formula. Fx equals to the sum from x0 to n, and n's derivative fx0 divide x factorial times x minus x0 power k plus a fraction of n factorial integrals from n0 to x0 to x, and x plus 1 derivative ft times x minus t power n dt. And let's recap. After we know the definition, let's recap the first fundamental theorem, integrating derivatives. We also learned the first fundamental theorem, integrating derivatives, in chapter 6. And that's the function f ab to the real number be continuous on the closed interval ab, and be differentiable on open interval ab. Moreover, suppose that its derivative, the first derivative f from ab to a real number is both continuous and bounded, and then we can conclude this formula that's integral from a to b. The first differential the first derivative fx dx equal to fb minus fa. And this formula also can be written as fx equal to fx0 plus integral x0 to x. The first derivative ft dt. And based on what we learned before, we can to prove the Cauchy integral reminder formula. We first integral the equation by parts, and we will see that the integral from x0 to x, the first derivative dt equal to minus integral x0 to x, first derivative ft, and derivative x minus t dt. Which equals to minus first derivative ft times x minus t, whose evaluation from t equal to x0 to t equals to x, plus the integral x0 to x, the second derivative of ft times x minus t dt. And last, we will have first derivative of x0 times x minus x0, and plus integral from x0 to x, the second derivative times x minus t dt. And from the formula, we obtain the Cauchy remainder theorem equation when n equals 1. The general formula follows by induction, and the inductive step depends on observing that if k greater than 1 and smaller than n minus 1, then the equation can be written as fraction k factorial times integral x0 to x, and the k plus 1 derivatives ft times x minus t power k dt will equal to minus fraction 1 over k plus 1 factorial times integral x0 to x. And k plus 1's derivative ft, derivative x minus t power k plus 1 dt. We will get the second equation by partial the first steps, because it can be written as minus 1 over k plus 1 factorial times f k plus 1 x0 times x minus x0 power k plus 1, and plus minus 1 k plus 1 factorial integrals n k plus 2 derivative ft times x minus t power k plus 1 dt. Finally, we will have the definition of the Cauchy integral remainder formula. That is fx equal to first derivative x naught times x minus x naught plus integral to the second derivative ft times x minus t dt, which is very familiar pattern similar to Taylor polynomial. And this is the references from advanced calculus by Fitzpatrick P. And that is all my presentation. Thank you for your listening.